Wood, tension, and a single string. A catastrophe model acts as an instrument, waiting for a skilled hand to draw out its meaning. We routinely commit billions in capital to withstand extreme events, yet our detailed historical records often span less than a century. We are building for a 500-year future using a dangerously thin past. In the mid-20th century, engineers began using mainframe computers to bridge this gap. They connected hypothetical hazard patterns with the built environment, creating a digital workspace for evaluating risk. These models provide a structured way to test our choices. They allow decision-makers to weigh different strategies when empirical evidence is no longer enough. Modern risk systems generate massive stochastic catalogs, reaching millions of simulated years. These computational events dwarf our observed history. A million simulated years is a set of assumptions played a million times, exploring the model's boundaries, but providing no new historical evidence. Simulation helps us find the limits of our own logic. To be useful, these catalogs require rigorous external challenge to ensure those underlying assumptions remain grounded in reality. The 1 in 100-year label has become the industry standard for probability. Because it sounds like a fixed schedule, it remains one of the most widely misunderstood metrics in risk management. A return period requires a finished sentence to have meaning. It relies entirely on the measurement frame, the variable, the duration, and the geography being tested. At this microscopic scale, a single 1-kilometer grid cell, a major hail strike is an extraordinary anomaly. As we pull back to a regional view, the math changes. A localized event that is rare at a single point becomes statistically common somewhere within thousands of cells math. Adding a financial layer shifts the perspective again. The physics of the storm must now interact with policy deductibles, building values, and insurance limits to produce a loss estimate. The final probability curve describes a specific intersection of hazard, geography, and financial perspective. The number changes whenever the parameters of the question change. Many organizations license multiple vendor models, hoping that a larger ensemble will provide a more certain consensus. This can create a false sense of diversity. When different software packages utilize the same climate datasets and intellectual lineage, they are simply reflecting the same underlying view. Robust systems prioritize independent structural views. They use challenger models built on different foundations to reveal where the primary model is fragile. Discovering disagreement among credible models is a signal of high performance. It pinpoints scientific uncertainty, turning ambiguity into useful information for the decision maker. At the point of decision, complex modeling outputs are often compressed into simple traffic lights: red, yellow, and green. There is a tendency to view a green score as a permanent physical property of a house. In reality, that color describes an action permitted under a specific set of rules. In this scenario, adding one more building to a heavily concentrated portfolio amplifies the insurer's existing tail risk. The building turns red because of its relationship to the surrounding policies. That same building becomes a green signal when placed in a sparse, diversified portfolio. Its physical vulnerability is identical, but its value to the organization has changed. A risk score is a contextual decision rule. It tells us how an asset interacts with an organization's specific strategy, existing book, and risk appetite. These interpretations guide the deployment of global insurance capital. They are the basis for engineering choices that protect cities and the built environment. High-performing teams include climatologists, engineers, and underwriters who actively hunt for model failure modes. They treat the software as a starting point for specialized review. A model's real validation happens through use. It proves its worth when it survives informed challenge and successfully convinces an organization to adapt its strategy. The instrument provides the capability, the tuning provides the precision, but the purpose of the system is the action that follows. A model sings when a person uses it to make a better, more resilient decision. True competence under uncertainty requires a learning loop that leaves the organization smarter than it was before. The model is the instrument. The better decision is the music.